All right, thanks everybody for coming today. My name is John Mumm. I'm a lead software engineer working on Wallaroo, an open source framework for writing stateful distributed streaming applications. But today I'm going to be talking about CRDTs and some of the mathematics that underlies them and how this theory helps explain some of their desirable properties. But let's start with a story. So imagine that you're out in the fields of Normandy and you've decided to spend a relaxing afternoon reading about CRDTs. And things are going great until all of a sudden you run across the monotonic joined semilattice. And you think, I wasn't really in for this sort of complexity today, I was just trying to relax, right? So you throw away your CRDT book and you pull out your trusty laptop and you say, I'm going to do something a little bit more fun today. I'm going to work on this new app. And this new app is called Birdwatch. And Birdwatch is the future of social media. It's a social media platform where users can post their best pictures of birds they've run across during their adventures. And here's an example. Our loyal user, Watcher302, has posted this image of a falcon. And you'll notice that users can interact with these posts by clicking this little bird icon in the bottom corner, right? And this post is doing pretty good because we almost have 1 million bird clicks here. Okay, so we as developers, we're interested in how are we going to actually implement this counter. And in particular, one of our important requirements is that we can continuously scale out. We intend to have so many users, we want to continue to be able to add servers to our network and so on. So one of the things that's important to us is that our clients can connect to one of many of these servers, right? And so it's a natural fit for implementing this counter is to think of it as a distributed counter that's distributed across some number of nodes in our cluster. So each of our nodes has some local view on the global count. Each one believes, hey, I think this is what the global count is right now. And we're representing it right now as these integers here. And as a bird click comes into a node, what the node is going to do is update its local counter, right? So a bird click comes in over here, one comes in here, one comes in here, and so on. And we're continuing to update. And then at some point, some user is going to hit refresh on one of these posts. And we're going to get a request asking us what's the total. And that request is going to come into one of these nodes. So if you notice, right now, our total doesn't reflect a lot of the information that's in the system. So what are we going to do to respond to this query? Well, let's coordinate. So what we do is we stop our node from processing, and we send out a request to everybody else. And then everyone else starts talking to each other, right? They add up their totals. They get 4, which is right now the global count. That's the correct answer for the entire system. And now we're ready to start responding to our request with the correct answer. I'm getting feedback here. But the problem is that coordination is slow, and it's complex. And the more nodes that we add to our system, the worse that this problem gets. In our case, though, coordination wasn't actually necessary. So if you think about Birdwatch, it's not really that important that our users get the latest, greatest information, the true answer for the entire system. In fact, it's much more important that as they check in on their posts, they get some feedback quickly to have a sense that there's engagement. They don't want to have to wait seeing 0 for a long time before they see that something has happened, even if the answers they do see are a little bit behind. Well, the nice thing about CRDTs is that we don't need this coordination if we're using them. In fact, we only need gossip to eventually converge on the truth. What this means is instead of having to stop processing and talk to each other and come to an agreement about the answer, what we can do is we can gradually, each node at its own leisure, pass this information around. No one has to stop to wait for this information. They can serve requests immediately. And order theory is the key to understanding how these convergent CRDTs work. So the good thing is that you can understand the relevant theory by building on familiar concepts. And that's what I'm going to do today in this talk. We're going to start from familiar concepts. We're going to build up to this idea of a joined semilattice. And then we're going to apply it to convergent CRDTs and see how it helps us understand how they work. So let's see a brief overview here. I'm going to start with order theory. I'm going to talk about total and partial orders. And I'm going to use these ideas to define a join according to an order. And then use all of this to define the joined semilattice. Once we understand what a joined semilattice is, we're going to look at how it helps us understand convergent CRDTs. We're going to see what a CRDT interface might look like, and we're going to implement a simple CRDT called a G counter. Finally, we're going to take everything we've learned and come back to address this question: what is a monotonic joint semilattice anyway? All right, so as I said, convergent CRDTs are perfect for asynchronous gossip. So why is this so? Well, you can merge them in any order. You can merge the same ones multiple times. And you can use them even if messages are delayed or reordered or duplicated. So we don't need strong guarantees for our network. And despite all of this, they always converge toward a global value. Now, they have all these desirable properties because they form a joint semilattice. And this is what brings us to order theory. So in order to understand joint semilattices, we're going to need three core concepts. We need to understand what an order is. We need to understand what it means for two elements to be incomparable according to that order. And then we need to understand what a join is. And I'm going to go through each of these in turn. So let's start with an order. An order is a binary relation on a set. So we can think of the familiar less than or equal to on integers, and we're going to represent this relation with this less than or equal to sign. So our ordered set could be the set of integers. Our relation could be less than or equal to, and it's going to look something like this. We write our integers left to right, 0, 1, 2 forever, and then we can compare elements in this set using our relation. So 1 is less than or equal to 5, and 2 is less than or equal to 4, 3 is less than or equal to 3. And the idea is that this relation is putting these elements in order, this left to right order. Now, one of these orders is total. If for any two elements in our set A and B, it's either true that A is less than or equal to B, or that B is less than or equal to A. Another way to think of this is we have a total order if we can compare any two elements in our set based on this relation. And the integers are an example, because we can pick any two integers and we can compare them using less than or equal to. So if we see this diagram, we have this diagram going upwards where the up arrow means that the thing above the other is greater than it, right? Or put differently, the one below is less than or equal to it. And here we can compare any of these two things based on our order. So 2 is less than or equal to 5, 3 and 4, 2 is less than or equal to itself, right? So this should be familiar. Now when it comes to CRDTs, we're more interested in partial orders. And a partial order is weaker than a total order. In particular, it does not require that every pair in our set can be compared according to our relation. And if A and B aren't comparable according to our relation, then we're going to write A is incomparable to B. So let's look at a couple of examples of partial orders. The first example we're going to look at is, what if we define less than or equal to as located in? So for example, we say New York City is located in the US, and we write it as New York City is less than or equal to the US. Okay, that works, but here, if we take New York City and Seattle, neither is located in the other, so we actually can't put them in this relation. So instead, we say they're incomparable. And we can draw a somewhat more complex looking diagram of a partial order. And we can do things like say, hey, can we compare the Earth and India? Well, yes, we can. India is located in the Earth. And notice that we're able to follow an arrow upwards in our diagram. Now we can ask the same question about Delhi. Is Delhi located in the Earth? Now we know the answer is yes, but notice that we can follow this path upwards from one node to another. And this is because our relation is transitive. So if something is located in something else, and that something else is located in something else, right, then this is located in that. And we're seeing that at work here. But now what if we tried to compare the US and India? Well, neither is located in the other, so we have to say that they're incomparable. We're never going to find a path in this diagram from one to the other. All right, so for a second example, let's think about our relation as happened before. And this is drawn from the distributed systems literature. So if we define our relation as happened before, then our set is going to be made up of vector clock timestamps. And a vector clock timestamp is a vector of timestamps. We're going to represent it as a vector of integers, where each integer, each element of the vector corresponds to a node in our system. So say we have two of these timestamps, v1 and v2. V1 happened before V2, so we write V1 is less than or equal to V2, if and only if every element in V1 is less than or equal to every corresponding element in V2. This is maybe easier to see with a diagram. So if we're trying to compare 135 and 146, then we see that 1 is less than or equal to 1, 3 is less than or equal to 4, and 5 is less than or equal to 6. All the arrows are going in the same direction. This means they're comparable and that 135 happened before 146. All right, let's look at a different example. Here 5 is less than or equal to 5 and 1 less than or equal to 2. But because 4 is not less than or equal to 3, because we've got an arrow going in the wrong direction, this means neither happened before the other. In the distributed systems literature, we'd say they happen concurrently. And in our case, we're saying they're incomparable. And we can draw a diagram like this. So imagine that we've chosen just this set of vector clock timestamps. This is an ordered set, and it's a partial order. We can draw a diagram like this, and we can now try to compare elements like we did before. So for example, we can ask, hey, are these two related according to our relation? And sure enough, we can follow a path upwards, and so it turns out that 110 is greater than 000. But if we take these two elements, they're incomparable to each other. All right, so we can't compare them, and we say they're incomparable. All right, now imagine we have one of these ordered sets, and we pick some subset P of that ordered set. So our ordered set might be all the integers, and our subset might be 2 through 4. An upper bound of P, an upper bound of that subset, is an element in S that's greater than or equal to every element in P. So if we go back to this example, 5 is an upper bound of P because it's in S, right, it's one of the integers, but it's greater than or equal, but all of the integers in our subset are less than or equal to 5. And 4 is also an upper bound because, again, everything is less than or equal to 4 in our subset, but 3 is not because 4 is in our subset and it's larger than 3. So we know that 4 and 5 are upper bounds, and it turns out that there are infinitely more of these as we keep going upwards. All right, so now let's go to a slightly more complex example. If our ordered set is this partial order on vector clock timestamps, and we pick this subset down here, the lower left corner, what are the upper bounds of this subset P? Well, 111 is one of the upper bounds because notice that we can follow these arrows up from all of our subset elements to 111. And the same is true for 110. Notice that it's less than or equal to itself, so that's fine. But these three are not because they're all less than 110. So in this case, these are our only upper bounds on this, because we don't have an infinite set here. These are our only upper bounds on this subset. All right, now let's say that our subset has only two elements, A and B. The least upper bound of that two-element subset is called the join of A and B, and it's written like this. So, for example, if our two-element subset is 1 and 4 here, we can take their join, and taking their join means what we're trying to do is find the least upper bound, the smallest element from S that for which all of these are less than or equal to that element. And in that case, it's 4. Now, if we take the join of 3 with itself, well, the smallest thing in S that 3 is less than or equal to is 3. So we stay where we are. And notice that when two elements can be compared directly, the join is the max of the two of them. So in this case, back to our partial order, if we try to compare these two through join, we notice that they're directly comparable, so the greater of the two is the join. But what happens if we take these two elements that are incomparable? Neither is less than or equal to the other, so the least upper bound on both can't be either of them. So what we're actually going to have to do is follow paths upwards until we find the smallest thing in our diagram here that's greater than both of them, or more strictly speaking, that they're less than or equal to. And that turns out to be 111 in this case. Now notice that whenever we take one of these joins, we're moving upwards in terms of our order. So let's see this in action. If we try to join the Bronx and Queens, neither's located in the other. We're back to our located in relation. So we have to go up in our diagram to find the smallest thing that's they're less than or equal to. That turns out to be New York City. And we can join New York City with itself. Well, it's less than or equal to itself, and it's the smallest thing that's true for. So we stay where we are. We can do the join with Ballard. Again, they're not comparable, so we follow our path upward. We can do the same with Mumbai in the US. They're incomparable. We follow the path upward, and we end up at the Earth. And this is what happened as we followed that trajectory. We moved up in our diagram, and we're able to write, for all the elements we've come across, we can write them left to right as being less than or equal to the subsequent one. Now, there must be only one of these least upward bounds for the join to actually exist. So what do I mean by this? Well, imagine that we're using this partial order descendant of. So we've got some grandparents and their children and their children's children who are cousins of each other. This is a partial order. So neither of the cousins are ancestors of each other. They can't be directly compared. So if we wanted to take their join, we're going to have to go upwards in our diagram, right? So we go up to the parents, and then we go up to the grandparents, but actually we have two least upper bounds in this case. So grandfather and grandmother, neither is larger than the other in our order. We don't have a join. We need a unique one in order for it to count as a join. Joins obey three laws that are all relevant to CRDTs. First, they obey associativity. This means it doesn't matter what order you take the joins in, you're going to end up with the same answer. They also obey commutativity, which means that no matter how we write this join, we're going to end up with the same answer. Finally, they obey idempotence. And this means that we can join the same element with itself over and over again, and we're never going to move from that element, as we saw with 3 and as we saw with New York City in that other example. Okay, so say we have one of these ordered sets. If we can find a join for every pair of elements in our ordered set, then we have a joined semilattice. So this is maybe a stricter definition. If this join x and y exists for all two-element subsets that include x and y, then S is a joined semilattice. So let's ask a question. Is this diagram right here a diagram of a joined semilattice? We can take some joins. These are directly comparable, so we know we can take that. These are incomparable, but we can follow our path upwards and we can get that. But if we try these two, there's nowhere to go. They're incomparable. There's no element in our set that we can get to that's a least upper bound on both. So it turns out this is not a joined semilattice. But if we were to simply add 1, 1, 1, then we would have a joined semilattice. We now can take the join of these two, and it's this upper bound on the diagram. And try to join any two of these, you're going to end up with an answer. And that's what makes it a joined semilattice. So with this in hand, we're now ready to look at convergent CRDTs. So I'm only going to be talking about state-based CRDTs in this talk. There's another type, operation-based CRDTs, and I'll give some links at the end, and I encourage you to read on. But for this talk, we're going to focus on state-based CRDTs. And these allow us to asynchronously share our nodes' local views. As we merge these CRDTs across nodes, they converge toward a global value. And each node is going to remain available to answer queries. And so this brings us back to our birdwatch application. So remember last time when we were trying to answer queries, we had to coordinate. This was a slow and complex process, and we thought, well, we don't really need this. So let's try to re-implement this using CRDTs. Imagine now that I have this example. So imagine that our intrepid user Watcher302 has posted this delightful image of a pelican. And it's only been 1 second, so right now there's 0 engagements, right? Now what we want to do is we want to implement our counter in such a way that as Watcher302 carefully refreshes his post over and over again to see how many engagements there have been, that there's at least some feedback, right? That there's some sense that people care. So what we're going to do is we're going to implement our system by putting one of these CRDTs on each of our nodes. And the CRDT is going to represent that node's local view, its belief about the global value of our counter. Right? So these are local views of global state. And if a bird click comes into a node now, it's going to update this local view. Now, I'm glossing over the details here, and we're going to get into them later. So just take my word for it for now. Then a bird click might come over there. It updates its local view. Now, our nodes can gossip to each other. This means that at their leisure, when they have a chance, they can pass their state along to the other nodes in the system. No one is blocking and waiting for this before they answer queries. But we sort of do it in the background. And when we do that, we send over the CRDT. And then our node that's received it merges it into its local view. And then, gossip is happening over here. And then maybe these two are gossiping while bird click is happening here. And this is all going on asynchronously. What happened? That's weird. We'll get somewhere. It doesn't matter. We can keep doing this. It's a good illustration. So on and so forth. OK, over time, our nodes are sharing information and converging toward a global value. Now when someone asks, hey, what's the total? Right? When someone's refreshed one of these posts and is looking for the number of clicks so far, we can answer immediately. So we send back the contacted node's local view. Now, our answer doesn't necessarily include all the information in the system, because meanwhile, other nodes could have been gossiping, could have been receiving bird clicks. But for birdwatch, we don't need that most up-to-date value. Right? So now imagine Watcher 302 comes back, excitedly hits refresh, and look at this. There have been 3 engagements so far in 5 minutes. Now, all the stats aren't in, so I don't know whether that's a good rate for birdwatch, but Watcher 302 is pretty happy because at least some people are paying attention. And Watcher 302 doesn't realize that actually the true count in the system is 4. But we'd rather serve our answer now, even if it's a little behind, because that keeps our users happy. It gives them a sense that people care, that they're giving them feedback of some kind. And this is all thanks to the magic of CRDTs. So for state-based CRDTs, we're going to need 3 things. We're going to need a state type that's ordered by some order, the sort of thing we've been talking about so far. And that state type is going to represent the local view of a node. We're going to need a merge function that we use to merge 2 of these CRDTs together. And this merge function has to act as a join on our state type. Finally, we need an update function. This is what we call when we get a bird click. We call this update function to mutate our state locally to capture that new information. Now, as we call merge on our states, the results should be converging towards a global value. And we can define this global value as the upper bound on our semi-lattice diagram. So imagine we have these 3 values. Now, if we think of all the ways we can merge them, that's actually going to give us our semi-lattice diagram. And it turns out to be this simple diagram here. The upper bound on this diagram is 7. So no matter how we merge these, we're going to eventually move upwards towards 7. Let's think about a partial order now. Imagine we start with these 3 values. No matter how we join them, we can draw from this sort of implicit semi-lattice diagram and move upwards towards this upper bound, which is the global value. And the join laws give us some nice properties here. Associativity and commutativity ensure that the order of merges doesn't matter. And idempotence ensures that we can merge in the same state multiple times. So this is where duplication comes in. Even if you accidentally send your state over multiple times, it's not going to matter. So if we again think of this diagram as having this upper bound, and that upper bound is our global value, then let's look at the way that it doesn't really matter what order we merge things in. Right? So if we were to merge these 2, these are incomparable values, so we have to move upwards in our implicit semi-lattice diagram. We get to this value, 110. These are directly comparable. We can move back to the greater of the 2. These are incomparable, and hey, we got to our global value. But we could have done this in a different order. We could have started with these 2, and their join is going to be 101. And then we could have merged it with itself. Doesn't matter how many times. The greater, the smallest thing in our semi-lattice diagram greater than, or that this is less than or equal to, is itself. And we can merge these 2, and we end up at our global value. Now, users of our distributed counter shouldn't have to worry about merging details. They should just be interacting with a simple interface. Right? The way they think of it is, I can either increment this counter, or I can request the value of the counter right now. In reality, our counter is going to be implemented across all of these nodes in our network. But to the user of the CRDT interface, that's not true. There's just one counter that they're interacting with. So imagine that they call value, and they get back 0. Right? Now, in our case, we only have increment, there's no decrement. So if they were to call increment 3 times on the counter, and then they called value again, they would expect the answer to be at least 3, because they saw 0, they incremented 3 times. Now maybe someone else somewhere else was incrementing, so it could be greater than 3, but they expect it to be at least 3, and in this case, sure enough, it is. But the real global value doesn't necessarily exist on any node in the system. It's the value toward which our merges are converging. Now, the idea is that it will eventually be reflected on all of the nodes. But because of these constant asynchronous updates, this eventually might actually never come. So there might never be a case, particularly as we add more nodes, where the true global value is reflected on one of the nodes. But that's okay as long as each local view changes over time in a way that makes sense to the user connected to that node. Okay, so now let's do it. Let's implement this G counter, what we're calling a G counter. And a G counter is a grow-only counter. Now, why do we want a grow-only counter? Well, Birdwatch is relentlessly positive, right? We want our users to be as happy as possible at all times. And nothing makes you less happy than seeing, hey, I got all of these engagements. Oh, wait, they went away, right? So we don't want that to happen. And then there's this other smaller reason that this happens to be a simple CRDT. Okay, we need these 3 things, if you'll recall. We need a state type that's ordered by some order. We need a merge operation that acts as a join for this ordered set. And we need an update operation that's used to update state locally. So how does this interact with our interface? Well, the user is just going to call increment and value, right? And these map pretty directly onto update and value in our CRDT implementation. Meanwhile, we've got this merge function that the user shouldn't have to think about. This is going on in the background. We're calling it asynchronously without the user even realizing it, gradually converging towards this global system-wide value. So let's start with a naive approach. What is it we're trying to do? We're trying to represent how many times this bird icon has been clicked in the system. So let's start with an integer, right? It's been clicked 100 times. We should be able to represent that as 100. Our update function can be increment, right? We add 1 to our local state, and value is just returning that increment. And now, okay, let's see, my node has 2. I've received 2 increments so far. Yours has received 5. So if I want to merge it in, what do I do? Well, maybe I add them together, because if I add them together, I'll get 7, and that is the right answer at that moment. So here are our 2 values, and we merge them together. We add them, and we get 7, and we're like, great, this is the right answer. And then this node shares with me again, and wait a minute, I ended up at 12, but there aren't 12 in the system. Well, the problem is the addition is not idempotent. And as a result, it can't act as a join. But earlier we saw that max was idempotent. Remember, with the less than or equal to relation on integers, if we took the join of 2 of them, it was always the greater of the 2, so it was max. So we know max does function as a join, so let's try that instead. All right, we're going to update our merge function, and let's see it in action. Now you might guess from the name where this is going, but we're going to see this in action, right? We get an increment here, we get an increment there, we get an increment there, and at this point, the value of the total should be 6 because the whole system has received 6 increments. All right, so let's imagine no more updates come in. We're going to simplify things. And we just start merging. We just start using our gossip protocol and sharing information. So we do the max of these 2 and we get 3. And we do the max of these 2 and we get 3. We do the max of these 2, and it looks like we've converged towards something, but it wasn't what we were looking for, was it? So the problem is it should have been 6, and we actually lost information as we were doing our merges. Because now, no matter how much information we share, we're never going to get beyond 3. So let's do this right. What we really need is for our local state to be a little more sophisticated than just an integer. So we're going to use a vector. And that vector is going to have integers in it. And those integers correspond to the number of time increment was called at one of the nodes in the network. And so, for example, this one means how many times an increment was called at node 0, and here how many times it was called at node 1, and here how many times it was called at node 2. And then each node is going to have a view on everyone's local count. right? So if your node has 105, that means you believe that increment was called once at node 0, 0 times at node 1, and 5 times at node 2. And then these beliefs might not be in sync, but that's the whole idea of the CRDT, is to allow this to asynchronously come together. So now our update function is going to be that we increment at the index for our local node. So for example, if we're node 0, when increment is called, we call update at index 0. And if it's called again, we call update at index 0 again, right? And then merge is going to be the coordinate-wise max, which will represent the latest value we know about the number of increments called at some node. So for example, we take the max of this, and this, and this, and this will be our merge. And the nice thing is that this is just the kind of join that we were looking at earlier. Finally, what is the value? Well, my vector is supposed to represent the number of times increment was called to each node, so I just add them up, and that gives me my latest information about the total in the system. So let's see this one in work. Increment comes in here at node 0, so we just increment our index, and so on at 1 and 2, right? And now again, we've got 6 increments in the system represented in this new way. So now let's imagine there are no more updates coming in, and we just start sharing our information through a gossip protocol, right? So we take the Cmax, the coordinate-wise max, which is going to be 320, and we do this over here. Again, the coordinate-wise max is now going to be 321. We merge here, it's 321. We merge here, it's 321, and it looks like we've converged on a value. And it turns out that no matter how much we share our local states, we're going to keep converging back on that same 321. And so when someone asks, hey, what's the value of the counter? What do? We add up these elements, we send back 6. Okay, I should note though that in reality, I've simplified things, but in reality now, I'm saying 6, but these other nodes could have received many increments in the meantime, right? So the idea is that the answers make sense to the user connected to this node. Okay, so that's a G counter. Now we could go on from there. There's many other types of CRDTs. So let's say that your company is not as relentlessly positive as Birdwatch Labs, right? That might be true. We can talk about it later. Maybe you want to allow decrements on your counter. You want to allow people to take back those engagements that's given so much lifeblood to our users. So you might want to implement this positive-negative counter. Or maybe you want to have some kind of invariant, like that the counter will never go below 0 on one of your nodes. Or maybe you want a register where you can represent some kind of arbitrary value, or a set, or a map, or a graph. There are CRDT implementations of all of these things, and they actually build on each other. A lot of them build on each other. So my hope is that with the tools we've gotten so far today, you can now go on into the literature, I'll give some links at the end, and see these implementations and understand why it is that each of them work. But for now, in the meantime, we're ready to tackle the dreaded monotonic join semilattice. So this term comes from the CRDT literature from the 2011 Shapiro paper I'll link to. It doesn't actually come from order theory, but what we're going to need is our convergent CRDT is going to need 2 properties to form one of these monotonic join semilattices. On one hand, our states need to form a join semilattice with merge acting as our join. And this is exactly what we've been looking at, so hopefully this is familiar by now. Now the other property is that our local update needs to move us monotonically upward in terms of our order. So this has been implicit, but I haven't talked about it. But the idea here is that no matter when we update and merge, we move toward a global value. All right, let's see this in action. So imagine these are our 3 values, right, in our system right now. If we were to keep merging them together, we're going to converge at this point towards 210. But let's say we call update over here. And so we're using our familiar update here. So we're just updating at our index. And now actually, all these, if we merge them together, will converge towards a new value. And then maybe we update over here, and then we'd be converging towards this new value, and so on. And notice that after we updated, we were always moving upwards in terms of our order. And now if we do our merges, we're going to keep moving up in the way we've looked at. And if we remerge old values, we end up here again, right? But let's try a slightly trickier example. So we're going to capture the fact here that updates and merges happen in parallel. I've been simplifying things and I haven't showed that yet. So now up in the top left corner, I've got the ghostly global value that might never exist anywhere, right? And so right now it's 321. It's the thing they would all converge toward. So if we merge these two together, we get 320, fine, that's familiar. And then over here we get an update, and that changes our ghostly global value to 322. And then maybe these two are merged, and look, they got to 322, so cool, we converged on our upper bound. But the thing is, meanwhile, there was an update over here which changed the ghostly value, right? And so now, if we merge these two together, cool, we got to it again, great. But maybe we've got a stale value around in our system, 001. Maybe that gets merged in with 420. What happens? Well, we're going to have to draw from our new implicit semi-lattice diagram. Notice our semi-lattice diagram is kind of shifting as this ghostly value shifts. And fortunately, we have one, 421. And if we merge that with this, cool, we got back to our ghostly value. So the idea is if we've got one of these monotonic joined semi-lattices, no matter how we update, no matter how we merge, we're always moving upwards. We're always converging towards some global value. And that's the concept. So here's my link to Kurion 2018 on my GitHub page. I've got a number of useful links. I've got that Shapiro paper I mentioned where they go through a number of implementations. I've got a paper on delta-based CRDTs where you don't ship around your entire state so they can be more efficient. I have a paper by Pat Halland about this idea that eventually consistent, you still might never actually see that thing you're eventually moving towards, and some other things as well. And that's it. Thank you.
So we have time for 2 free questions.